An alternating current waveform can be shown graphically. This is the waveform of one cycle, that is, one complete revolution of the magnet. It plots changes in EMF against the rotation of the magnet. The value of the induced EMF depends on the strength of the magnetic field. Increasing the strength of the magnetic field increases the value of the induced EMF. It also depends on the speed at which the magnet rotates and on the number of turns of wire on the stationary coil. This simple model has only one stationary coil. This is called single phase. In a real automobile alternator, 3 separate coils of wire or phase windings are common. The windings are arranged so that when the magnet is rotated, it generates a 3-phase output. The phases are equally spaced in time, and this results in a phase shift of 120 degrees. The alternator consists of a stationary winding assembly called the stator, a rotating electromagnet, the rotor, a slip ring and brush assembly, a rectifier assembly, 2 end frames, and a cooling fan. A voltage regulator monitors battery voltage and varies current flow through the rotor field circuit and thus controls the strength of the rotating magnetic field. This keeps system voltage to a safe level. This section examines rectification. Automotive alternators use diodes in the rectifier assembly. A diode allows current to flow in the forward direction, but blocks the flow of current in the reverse direction. This is a 3-phase bridge rectifier. It has 6 diodes to rectify the total alternator output, 3 positive and 3 negative. One of each is used to rectify current in each of the 3 phase windings. The positive diodes let current flow out to the battery terminal B positive. The negative diodes complete the return circuit from the battery terminal B negative. In each revolution of the magnet, the polarity of each phase winding changes, and as a result, the current changes direction. To provide a unidirectional or DC output, a complete circuit is needed for current to flow when each change in polarity occurs. Let's look at the action of just one phase. As the rotor turns, it induces a voltage in the winding, which generates current flow. In this position, and with this polarity, the current path is as follows. Output of winding A, positive diode A, alternator terminal B positive, battery positive terminal, battery ground B negative, alternator ground, negative diode B, output of winding B, neutral or star point. When the magnet rotates further to this position, the polarity of winding A changes. The current path then is winding A at star point, winding C, positive diode C, alternator terminal B plus, battery positive terminal, battery ground, alternator ground, negative diode A, and output of winding A. As the rotor moves through its various positions, individual phase currents change in magnitude and polarity, but the output current to the battery and the electrical circuits remains unidirectional. This section examines connections of the phase windings. 2 methods of connection can be used for the stator or phase windings: star or Y connection and delta connection. In the star method of connection, one end of each phase winding is taken to a central point where they are connected together. This is known as the star or neutral point. The other end of each winding is connected in the bridge rectifier circuit between a positive and a negative diode. Each winding is then always part of a complete circuit. In the delta method, the windings are connected in the shape of a triangle. Connections are then taken from each point of the triangle to the bridge circuit. This section examines the rotor circuit. Current is provided to the rotor by means of the slip rings and brushes. When the engine is running, most alternators supply the field current directly by means of 3 extra diodes connected to the bridge rectifier circuit. Extra diodes are known as field diodes or excited diodes, and the alternator is said to be self-exciting. However, this self-excitation can only occur when the alternator is producing an output. When the ignition switch is closed, current can flow from the battery positive terminal through the ignition switch and charge indicator lamp to the L terminal of the alternator. The circuit is completed through the slip rings and rotor field winding, and through the voltage regulator to ground on the vehicle frame. The small amount of current flowing in the circuit illuminates the indicator lamp and provides the initial excitation of the field winding. This magnetizes the rotor pole shoes and produces a weak magnetic field. When the rotor is driven by the engine crankshaft, the rotating magnetic field induces a voltage in the phase windings, which is applied to the B positive alternator output terminal. However, this voltage is also impressed on the excited diodes, and current can now flow directly to the field circuit, restricted only by the resistance of the field winding. This strengthens the magnetic field, and the output voltage rises quickly. The voltage regulator now takes over to control the field circuit current and maintain a preset regulated output voltage at the B positive terminal of approximately 14 volts. As the voltage on each side of the charge indicator lamp is now equal, there can be no current flow through the lamp and the lamp is extinguished. The alternator is now set to be charging, and since the output voltage at the B positive alternator terminal is greater than that of the battery, the current flows to the battery to begin the recharging process. This section examines alternator voltage regulation. When the engine is running and voltage output is low, the regulator switches the rotor circuit to ground and maximum current flows through the rotor field winding. The high-intensity magnetic field created raises the value of the induced voltage in the stator windings and alternator output rises. The output voltage is also impressed on the excited diode circuit, and the output voltage is sensed by the regulator control circuits via the regulator L terminal. When the maximum allowable voltage has been reached, the control circuits switch the rotor field circuit off, and the magnetic field at the pole shoes reduces in size or decays. The decaying magnetic field reduces the magnitude of the voltage induced in the stator windings and lowers the alternator output voltage. This again is sensed by the voltage regulator control circuits, and the rotor circuit is switched on once more. The regulator switches rapidly between the on and off conditions, within the preset maximum and minimum voltages, to allow the alternator to maintain an output voltage of approximately 14 volts, and at the same time, deliver the current needed for electrical system operation. As lights and other accessories are turned on and the load on the system increases, the current output to the circuits must be increased and the output voltage must be maintained. The regulator again adjusts the rotor field circuit, but this time increases the current flow and therefore the magnetic field strength. The induced voltage in the stator rises to maintain system voltage and increase current output. There is no need for a current regulator, as the design of the stator winding determines the maximum current output of the alternator at a system operating voltage of 13.8 to 14.2 volts. If an alternator is rated at 40 amps, it is capable of maintaining a system voltage of 13.8 to 14.2 volts up to a current load of 40 amps. This section examines starter motor switching. The starter motor is usually brought into operation by activating a starter switch as part of ignition key operation. This remote control operates a starter-mounted solenoid which has two functions. It acts as a solenoid to engage the pinion with the flywheel ring gear, and it acts as a relay to bridge the main starting terminals. In the control circuit, the ignition lock start switch has a positive connection from the battery and a connection to two windings in the starter solenoid. One of these is a pull-in winding, which has a low resistance value, and the other is a hold-in winding, which has a high resistance. The pull-in winding is connected to the main starter terminal leading to the field and armature windings, and its circuit will be completed through the armature to ground on the starter casing and by frame return to the negative battery terminal. The hold-in winding is connected to ground on the starter casing. With the ignition key in the start position, current passes from the positive battery terminal through the start switch and through both windings. The high current flow through the low resistance pull-in winding creates a strong magnetic field which attracts the solenoid plunger towards the main terminals. Plunger movement also operates the shift fork lever, engaging the pinion with the ring gear. The plunger contacts a switching pin, which transfers the motion through a contact spring to a moving contact, which then bridges the main terminals. This allows a large current to flow from the battery through the starter motor windings, causing armature and pinion rotation and rotation of the engine crankshaft. Bridging the contacts also short-circuits the pull-in winding, and the plunger is held in position by the action of the hold-in winding only. The pull-in winding is short-circuited because battery voltage is now being applied to both sides of the winding, and this stops current flow through it. During engine cranking, the action of the helix on the rotating armature shaft causes the pinion to be forced as deeply as possible into the flywheel ring gear, and this holds the pinion in mesh. The hold-in winding is only used to ensure that the moving contact continues to bridge the main starter terminals. When the engine initially fires, the ring gear tries to drive the pinion and the force acting through the helix is relieved. When the starter switch is released, this opens the circuit between the battery and the hold-in winding, and current flow through the winding ceases. The return springs in the solenoid return the plunger, the moving contact, and the pinion to the rest position. In headlights, two filaments are necessary to provide for a main and a dip beam function. These must be positioned correctly in relation to the highly polished reflector. This is called focusing and is carried out during manufacture. The main or high beam filament is positioned at the focal point of the reflector to project the maximum amount of light forward and parallel to the reflector axis. This light is then shaped by the lens, which is made up of many small glass prisms fused together. These prisms bend the light horizontally and vertically to achieve the desired pattern for road illumination. The dip or low beam is placed above and slightly to one side of the main filament. Mounting the dip filament in this position produces a beam of light that is projected downwards and towards the curbside. With this arrangement, the main filament produces the best possible light output, while the dip filament gives a downward and dispersed beam, which should not dazzle oncoming drivers. A semi-sealed beam headlight uses a replaceable bulb with a pre-focus collar. The collar locates the bulb in the headlight and also controls the correct positioning of the filaments. A sealed beam headlight has a highly polished aluminized glass reflector, which is then fused to the optically designed lens. This forms a completely sealed unit which has the filaments accurately positioned in relation to the reflector. When a filament fails in a sealed beam light, the whole unit must be replaced. Some headlight bulbs have a partial shield below the dip filament. This shield stops light from the filament striking the lower part of the reflector. The shield provides the primary shape of the dip beam. The final shaping of the beam is carried out by small cylindrical shaped prisms in the headlight lens. This provides a dipped beam that is asymmetrical. All bulbs have letters and numbers stamped on the bulb, which indicate the power consumed by bulb operation at the nominal operating voltage. In this 12-volt 21-watt bulb, the filament will consume 21 watts of power when 12 volts is applied across the filament. While the wattage is not necessarily an indication of light output, it can be generally assumed that the higher the wattage, the greater the light output will be. This section examines parking and tail light circuits. For motor vehicles and trailers, two red tail lamps operate when the headlight switch is in the park position and the headlight position. The two lights are located close to the widest points of the vehicle, so that the vehicle width can be seen by other road users. The bulbs are connected in parallel to each other so that the failure of one filament will not cause total circuit failure. A number plate illumination lamp is usually connected in parallel to the tail lights and operates whenever the tail lights are on. The tail lights are usually incorporated in a cluster assembly at the rear of the vehicle. Government regulations control the height of the lamps and their brightness. The park lights, sometimes called clearance lamps, are located at the front of the vehicle and are used at night time when the vehicle is parked on the side of the road. They use low wattage bulbs and may have a lens or diffuser that makes the emitted light widespread. In some cases, the park lights are incorporated in the headlight assembly. The park lights operate when the light switch is moved to the first position. For safety reasons, the park and tail lights continue to operate when the light switch is moved to the headlight position. The bulbs are connected in parallel with each other. The circuit for the park and tail lights includes the battery, fusible links and fuses, park light switch, the lights at each corner of the vehicle and the number plate light, the wiring to connect the components together, and the ground circuit to complete the circuit to the battery through the vehicle frame. When the park light switch is closed, current flows from the battery through the fusible link to the park light switch, where it is fed through the fuse to the front park lights and to the rear tail and number plate lights. After passing through the filaments, the current path is completed through the frame of the vehicle to the negative battery terminal. This section examines headlight circuits. Bright, well-adjusted headlights are necessary for safe vehicle operation at night. The main beam provides a bright light suitable for driving on open country roads. The dip beam only is used in built-up areas. In country areas, the dip beam is used whenever oncoming traffic could be dazzled by the main beam. The headlight circuit consists of the battery, fusible link and fuses, headlight switch, headlight relays, dipper switch, headlights, high beam indicator light, wiring of a suitable size to carry the electric current through the circuit, and the ground circuit. When the headlights are switched on, current is applied from the battery through the fusible link and fuse across the closed switch contacts to the dipper switch. In the dip beam position, electrical current can flow from the dipper switch contacts through the low beam relay winding to ground. This creates a magnetic field that closes a set of contacts. Closing the contacts allows electrical current to flow from the battery through the fusible link to the relay contact. From the closed relay contacts, the current flows to the light filaments and then to ground. The park and tail lights are also in operation when the headlights are switched on. This section examines stoplight circuits. Stoplights are red lights fitted to the rear of the vehicle. They are usually incorporated in the taillight cluster, although many vehicles have a higher additional stoplight mounted on the top of the boot lid or on the rear window called a high-level stop lamp. The stoplights are activated whenever the driver operates the foot brake to slow or to stop the vehicle. The circuit consists of the battery, fusible links and fuses, a stoplight switch, stoplight bulbs, wiring to connect the components, and the ground circuit to return current from the filaments to the battery. When the operator of the vehicle depresses the brake pedal, a switch mounted on the pedal support is closed. This allows electrical current to flow from the battery through the fuse, through the switch, to the brake light filaments and to return to the battery by the ground system. When the driver releases the pedal, it returns to the rest position and open circuits the stoplight circuit. The flow of electrical current stops and the brake lamps are extinguished. This section examines the reversing light circuit. The reversing lights are white lights fitted to the rear of a vehicle. They provide the driver with vision behind the vehicle at night and also alert other drivers to the fact that the vehicle is to be reversed. The circuit consists of the battery, fusible links and fuses, the ignition switch, the reversing light switch on the transmission, reversing light filaments, wiring to connect the components, and the ground circuit to allow current to return to the battery through the vehicle frame. When the ignition switch is on and the vehicle is placed in reverse gear, current flows from the battery through the ignition switch to the closed reversing light switch on the transmission. Electrical current flows across the closed switch to the reversing lights and then returns to the battery by the earth return system. This section examines the indicator or turn signal circuit. Indicators are amber lights located on the extreme corners of the vehicle. A column-mounted switch operated by the driver directs a pulsing current to the indicator lights on one side of the vehicle or the other. These pulsing lights warn other road users of the vehicle's intended change of direction. Once activated, they continue until the switch is cancelled, either by the operator or by a cancelling mechanism in the switch. The cancelling mechanism operates after a turn has been completed and the steering wheel is returned to the straight ahead position. The circuit consists of the battery, fusible links and fuses, the ignition switch, the flasher unit, a 3-position switch used as the direction indicator switch, the lights at the front and rear of the vehicle, pilot lights mounted in the instrument cluster to indicate to the driver which way the switch has been operated, wiring to connect all of the components, and the ground circuit to return the electrical current to the battery. If the indicator switch is turned to indicate a right-hand turn, current from the battery flows through the fusible link to the ignition switch, where it is directed through a fuse to the flasher unit. The flasher unit uses a timing circuit to pulse the current flowing out of the flasher unit 60 to 120 times per minute. This pulsing current is directed through the indicator switch to the right-hand indicator lights at the front and rear of the vehicle, causing the lamps to flash on and off. A pilot light on the instrument cluster also pulsates. The operation of the flasher unit also produces a clicking sound to warn the driver that the indicators are in operation. When the indicator switch is returned to the off or central position, no current flows through the flasher unit, so the timer circuit is switched off. When the indicator switch is turned in the opposite direction, it directs the pulsing current to the left-hand lights at the front and rear of the vehicle, as well as the left-hand pilot light on the instrument cluster. Most modern vehicles now are equipped with hazard warning lights. This circuit is similar to the indicator lights, except that it simultaneously causes a pulsing in all exterior indicator lights and both pilot lights on the instrument panel. These can warn other road users that a hazardous condition exists, or that the vehicle is standing or parked in a dangerous position on the side of the road. This section examines automotive circuit diagrams. A complete electrical diagram for the lighting systems of a vehicle can be built up from the separate lighting circuits that are discussed on this disc. This is the circuit for the park and tail lights. To this circuit, we can add the circuit for the headlights and dip circuits. Include the stop light circuit, the reversing light circuit, and indicator circuits. The completed circuit is a wiring diagram for the external lighting of a motor vehicle. This section examines the rotor. It consists of a coil of wire wound on an iron core and pressed on a steel shaft. An iron segment is fastened on each side of the coil assembly so that the projections or claws interlace. The ends of the rotor coil are connected to insulated slip rings mounted on the shaft, and spring-loaded brushes maintain contact with the slip rings at all times. When a current is passed through the slip rings and the coil winding, it establishes a north and south pole at the ends of the iron core and the shaft. The projections then take on the same polarity as the end of the shaft on which they are mounted, and this forms pairs of north and south poles around the rotor circumference. The rotor usually has 8 to 12 poles, which are tapered to reduce noise as the rotor rotates. This section examines the stator. The stator is mounted between the two end brackets. It consists of a cylindrical laminated iron core which carries the three-phase windings in slots on the inside. The windings are insulated from each other and also from the iron core. They form a large number of conductor loops which are each subjected to the rotating magnetic field. This section examines the two end frames. They are normally made from aluminium and form housings to accept the bearings which support the rotor at the drive end and at the slip ring end. Ball bearings are normally used at each end. This section examines the slip ring and brush assembly. Slip rings are normally copper bands molded onto an insulating material, then pressed on the steel shaft of the rotor. Each end of the rotor winding is connected to one of the copper bands, so that as the rotor rotates, the brushes can make a connection with each end of the winding. The brushes are made of a combination of copper and carbon and are carried in brush holders mounted in the end frame. This section examines the rectifier assembly. The diodes for rectification are mounted on heat sinks in packs of 3. One heat sink has 3 positive diodes and the other has 3 negative diodes. The positive diode heatsink is insulated from the frame and is connected through the output terminal to the battery positive or B+ terminal. The negative diode heatsink is connected to the frame, and this allows the return circuit via the battery negative terminal to be completed. This section examines the alternator's cooling fan. This fan is a powerful centrifugal type. It is mounted on the rotor shaft and may be an integral part of the drive pulley or part of the rotor. It is essential to maintain a cooling stream of air over the diodes and stator. This section examines starter motor construction. A basic starter motor consists of a direct current motor, a drive pinion with an overrunning clutch, and a drive pinion engagement solenoid and shift fork. The armature is the revolving component of the direct current motor. The armature shaft is supported at each end by bushes pressed into end frames, which locate the armature centrally in the outer casing or yoke of the motor. The commutator end frame carries the copper-impregnated carbon brushes, which conduct current through the armature when it is being rotated in operation. The brushes are mounted in brush holders and are kept in contact with the commutator by tension spiral springs. Half of the brushes are connected directly to the end frame and via the ground return of the vehicle frame to the battery negative terminal. The other half are insulated from the end frame and connected to the positive battery terminal via the main starter solenoid input terminal. This can be a direct connection in the case of a permanent magnet type starter, or indirectly via the electromagnetic field poles of a series wound motor. The electromagnets are formed by current flow through heavy strip copper windings, wound around iron pole shoes which are fastened to the yoke. Permanent magnets are located similarly, but occupy less space. The yoke is made of iron and serves to concentrate the magnetic field produced by the field magnets. Starter motors with electromagnetic field windings for light vehicle applications are series wound motors. Because the resistance of the field and armature windings is low, the current flow is high when the motor starts under load, and this generates a strong magnetic field that will produce a high turning effort at low speeds. This high initial torque drops sharply as motor speed increases due to the back EMF induced in the armature windings, which opposes current flow and reduces torque output. Some series wound motors have the field windings in parallel with each other, but then in series with the armature. These are referred to as a series parallel field series motor. By connecting the field windings in this way, more current can flow in the circuit and an overall increase in torque is obtained. Engagement is provided by operation of the ignition switch in the start position, which activates a starter-mounted solenoid whose plunger is engaged with the hooked end of a pinion shift lever and operating fork. Solenoid operation moves the operating fork, causing the pinion to engage with the ring gear and also causes the plunger contacts to bridge the main starter terminals. The fork locates in a guide ring on a pinion driver, which is coupled to the pinion via a roller-type overrunning clutch designed to transmit drive in one direction only. The pinion driver is mounted on a helix machined on the armature shaft to form a very coarse thread. This allows the pinion driver to rotate slightly when it is moved towards the ring gear, and this feature, together with a chamfer on the leading edge of the ring gear and pinion teeth, is designed to assist meshing and easy engagement. However, if the pinion teeth butt against the ring gear teeth and engagement is prevented, the guide ring continues its axial movement by sliding over the sleeve of the driver and compressing a meshing spring until the plunger contacts bridge the main terminals and the armature begins to turn. Slight armature rotation and the force from the meshing spring allows the pinion teeth to drop into mesh with the ring gear, assisted by the screw action of the helix. The helix forces the pinion further into the ring gear until the pinion contacts a stop ring on the armature shaft. This prevents further axial movement, and the driver and pinion now lock to the shaft via the helix and overrunning clutch and transfer the armature rotation to the flywheel. The pinion has only a small number of teeth compared to the ring gear, and this means the armature will rotate several times for each revolution of the flywheel. The gear reduction also multiplies the torque from the starter motor. As soon as the engine starts, its rotational speed will eventually exceed the speed of the armature. At this instant, the overrunning clutch breaks the connection between the pinion and the armature shaft and prevents overspeeding and damage of the armature. The pinion remains meshed as long as the engaging lever is held in the engaged position. Releasing the starter switch allows the solenoid plunger return spring to return the engaging lever, driver, and pinion to their original position. This section examines commutation in the starter motor. When current flows in a conductor, an electromagnetic field is generated around it. If the conductor is placed so that it cuts across a stationary magnetic field, the conductor will be forced out of the stationary field. This happens because the lines of force of the stationary field are distorted by the electromagnetic field around the conductor and try to return to a straight line condition. Reversing the direction of current flow in the conductor will cause the conductor to move in the opposite direction. This is known as the motor effect and is greatest when the current-carrying conductor and the stationary magnetic field are at right angles to each other. A conductor loop, which can freely rotate within the magnetic field, is the most efficient design. In this position, when current flows through the loop, the stationary magnetic field is distorted and the lines of force try to straighten. This forces one side of the loop up and the other side of the loop down. The motor effect causes the loop to rotate until it is at 90 degrees to the magnetic field. To continue rotation, the direction of current flow in the conductor must be reversed at this static neutral point. A commutator is used for this purpose. In this example, the commutator consists of two semicircular segments which are connected to the two ends of the loop and are insulated from each other. Carbon-impregnated brushes provide a sliding connection to the commutator to complete the circuit and allow current to flow through the loop. Rotation commences with both sides of the conductor loop cutting the stationary field. When the loop passes the point where the field is no longer being cut, the momentum of rotation carries the loop and the commutator segments over, so that the brushes maintain current flow in the same direction in each side of the loop relative to the stationary field. This process will maintain a consistent direction of rotation of the loop. In order to achieve a uniform motion and torque output, the number of loops must be increased. The additional loops smooth out the rotational forces. A starter motor armature has a large number of conductor loops, and so has many segments on the commutator.